Okay, so Espen, the next speaker is the CEO of EM Logic, a design center for embedded system and FPGA in Norway. He's graduated from University of Glasgow in Scotland and has 30 years experience with the FPGA and ASICs development from various companies, both in Norway and in Switzerland with Philips Semiconductors. He's also the author and architect of UVVM, the fastest growing FPGA verification methodology worldwide, and he will introduce us to this nice tool.
Right, thank you. Is it on? Is it working? Yeah? Yeah. Good. You can hear me, right? Yeah, good. Okay. So thank you for the introduction. And just briefly before I start, I'll just briefly mention that I come from a company called EM Logic. It's an independent design center based in Norway. We only have Norwegian customers. Established 3 years ago. Now we are 43 developers, 18 on FPGA. And we are a verification IPM methodology provider for UVVM. Also do design and verification courses separately on FPGA worldwide. So what is UVVM? So it's a universal VHDL verification methodology. It's a library and methodology for FPGA, ASIC, and CPLD. It's free, open source. It is very structured infrastructure and architecture, and most important, or more important, is that it allows you to make your test bench with a good structure and infrastructure. It significantly improves certification efficiency and assures a better design quality. And that's the target of this tool. It's recommended by Doulos for test bench architecture. We are now in our third project with ESA to extend the functionality of this library. So we work tightly with ESA. It's available on the IEEE SA Open standards, and it runs on any VHDL 2008 compliant simulator. And it's downloadable from GitHub as well. So I guess some of you have seen this before. It's from the Wilson research showing that nearly half of the project time is spent on verification. That's a long time. And of course, the more complex and the more safety related, the more mission critical it is, the more verification you have to do. And the question here is, could verification time be reduced without reducing the quality? Another graph here, which is also important from Wilson research, is when you look at verification, you actually spend half the verification time on debugging, and that's not good at all. That means you have a lot of issues in your test bench, in your design, and you also spend a lot of time debugging those issues. And I think we can definitely be more efficient, more structured here. So I'm talking about quality and efficiency here. And I think these are the most important things, whatever you're doing, whether it's design, verification, software, hardware, whatever. You have to have overview and readability. That's the most important. Then you have to have modifiability, maintainability, and extensibility, because you always change your design. You always need to modify it. Then, of course, as I mentioned on the previous slide, debuggability is extremely important as well. And, of course, everybody wants reusability. And this has been basically the target when we made UVVM. And this is the total UVVM system with all the parts in this system. In this presentation, I was thinking maybe I should just do a basic introduction of the basic parts, but I decided I would cover most of these parts so you get a good impression of what is actually inside UVVM. So I'll start with the basic stuff, what we call utility library. There's an infrastructure. And in this case, it's a dead simple device in the test, an interrupt controller, clock and a reset, and interrupt to the CPU, number of interrupts coming in. And this SPI is a simple bus interface. Looks like the old RAM interface, dead simple, single cycle. And of course, you want to make a test bench for that. And the first thing you need in that test bench is to generate a clock. So you need a clock generator. And then from utility library, you can directly instantiate a procedure, a clock generator procedure. And remember that when you instantiate a procedure in VHDL directly in the architecture, that's exactly the same as a process. So that's a really, really good way of reusing processes. So just pull that directly out of the library and instantiate that. And of course, lots of different variants of that. But then you have clock generator. And then you have your test sequencer that is basically going to test everything inside your device in the test. And I'm just going to show you some of the main commands that you would use in any design here. So, for instance, you always should log what you're doing because that's important for debugging. It's important for anyone who wants to run that test bench. And it's important to see the progress and develop your test bench. So we have something called a log command. And in this case, we're just telling what you're doing. And then in the blue below here, you can see the transcript, how it is in the transcript or in the log file as well. So that shows up with a timestamp in the transcript. Then, of course, what you do in a test bench is always to check values. In this case, we're checking that the value of interrupt to the CPU is 0. And then we have a mandatory comment, a message after that. And that's part of the methodology because I think we should really force the designers to make a comment when you do a command. Of course, you could just make an empty, double quotes here, empty string. Basically, if you do that, then you're saying that if you don't understand this, you're stupid. So I think it's good to have a comment there because you don't always understand what other people mean when they make a test bench. Then you want to check for stability, and you don't want to check a value over and over and over again. You want to check that it has been stable for a given time with no spikes, no pulses or whatever. So in this case, you set a timestamp, in this case, for instance, at the reset time, and then do a check stable, that the interrupt to the CPU has been stable from now back to this reset time. And then you also get a positive acknowledge on that in the transcript. Then you generate pulses for the interrupts, and you get a log for that as well. Then another thing which is extremely important in any test bench is to wait with a timeout. Never wait without a timeout, because then what happens is that when the event you're waiting for doesn't occur, then you're going to wait forever, and you have absolutely no idea why you're waiting. This wait value waits for the interrupt to the CPU to go to 1 at the earliest after 0 nanoseconds, at the latest after 2 clock periods. And then you get a message that it's done as well. Then lots of other commands as well. I'll show that on the next slide. But I also want to show that a normal part of this would also be to do BFM accesses, to access the interfaces with bus functional models. So in this case, we do an SPI write. SPI, remember, was this simple bus interface. So writing AA to the address, to the register ITR, interrupt trigger register, inside that module. And then you also get a message saying you did that. So this is a simplified transcript. We have a prefix, message ID, and scope that could also be shown here, but that would be, you wouldn't see it in the back row. Sorry. Yeah. The last thing that is said there was that all these checks comes with a positive acknowledge, but all these positive acknowledges can be filtered out with verbosity control, so that you don't basically get 10,000, 100,000 of these messages when things are working. This is just a list of other commands that's available in this library. And this is the basic utility library. I think the most important ones here are the different kind of clock generators, checking for stability, generating pulse, and blocking flags, barriers, and so on and so on. Then, one step up, you want to access these interfaces. I mentioned this simple bus access, simple bus write. This is an example showing a UART. And again, you can use the BFMs provided with the utility library for that. So we can do a UART transmit of 2A, for instance, and then that will be written into the RX interface on the RX protocol, into the UART, and of course end up in the RX register. And then you can read that out of the UART with an SBI check. In the transcript, you would get a transcript of the UART transmit and on the following check. Same thing you can do on the output as well. You can do an SBI write to the TX register of the UART, and then, of course, you would expect data to come out of that interface sometime later on the UART format. So if that works fine with the SBI write, you'll get a good message for that. But this is just showing what will happen if there's a mismatch on the expected data. So in that case, you get a mismatch report saying that the value was so-and-so, whereas we expected so-and-so. And also gives you the message that you provided yourself into this command. There are free open source BFM for lots of different interfaces. So these are available right out of the box from this library. And all well documented. So I talked about BFMs, and BFMs are excellent, but they're not good enough in all cases. So in this case, for instance, they are great for simple test benches. You might even think it's good for UART, great for UART. And it's good for UART. It's not great for UART because there are lots of corner cases you cannot check if you're just doing one sequencer with BFMs. So because BFMs are great, they are dedicated procedures in a simple package. You just reference them and call them from a process. Problem is that a BFM or a process can only do one thing at any time. It can either execute that BFM or another BFM or do something else because it's just a single thread. So to do more than one thing, we need an entity or a set of processes. And this is what we call the verification component. We call them VVCs, the VHDL verification components. So they're basically verification components with extended functionality, and I'll just go into that now. So what we basically do then is we have the test case sequencer not accessing the bus interface via the BFM, but via this verification component instead. So we have an SBI verification component here. And the contents of that is like this. It has an interpreter, a command queue, and an executor. That's the base architecture of all verification components. The interpreter will look at the command coming from the test case sequencer and check, is this command for me? If so, is it to be queued or is it to be executed immediately, like, for instance, flush the queue or something? But if it's to be, queued, it will put on the command queue. The executor will see it. It will fetch it from the queue. Then the executor here will case on what to do. Could that be an SBI write, an SBI read, an SBI check, or something else? And then it will execute the BFM we talked about previously towards the bus interface. So that means now the test sequencer is not executing the BFM, but the verification component is executing the BFM and has been told to do so. So how is that? How does that happen? This is example with the BFMs using just basic procedures, SBI write and UART expect. And this is the situation with verification components, now with verification components on all the interfaces. And this would be then the syntax for that. Exactly the same syntax as for the BFMs, but the difference here is that you have to tell the system which verification component should execute this command. So that means we have to add a few more parameters. For the SBI, we have to say it goes to the SBI verification component target, instance number 1, because of course there could be multiple instances of that. And for the UART, we also added RX and TX parameters. So that's basically the only difference you'll see in the test sequencer. But these verification components, as I said, they are not just the BFM, just an execution of that. They have additional functionality, like, for instance, delay insertion, command queuing, completion detection, and so on and so on. lots of additional functionality that makes these verification components much more worthwhile for the designer. And once you have a component like this, it's easy to extend, and that's important. So we can then extend this with lots of different things. I mentioned we can case on what to do. That could be a write, a read, and a check, for instance. But it could also be write 100 random data, for instance. That could also be a command that could provide to the system. It's easy to add checkers and monitors, so you can build those into the verification component and enable them whenever you need them. And I think the most important thing of all is the way it allows you to handle split transactions. Because split transactions is a problem in most test benches. Basically what you have there is you're doing, for instance, on Avalon, you do a read request first, and then you could do multiple read requests before you get the first response back, and then you do a read response. That's a split transaction. In this case, what will happen is that the first executor will execute all the read requests, and then pass it on, the same command that it got in the command queue there, pass it on to the FIFO there, and then the response executor will be handling those in order, all the read responses. And that means it's an extremely structured way of handling split transactions. And you can even do this for out-of-order transactions if there's a queue there and not a FIFO. Let's look at this verification component-based test bench with an AXI stream, for instance. Then in this case, it could look like this. In this case, we have a FIFO with an AXI stream interface. Then we have an AXI stream master interface on one side and a slave interface on the other side, of course, and also a clock generator. And then we have our main test sequencer. So what we do first here is an AXI stream transmit, and we're telling the system which one we're talking to. That's the AXI stream verification component, instance number 0 in this case. And we provide a data array to that. And then we can also talk to the test sequencer can also talk to the receiving AXI stream slave in the other side and tell that to expect this data array. And then what happens is that data is provided through the device in the test, ends up on the slave AVC, and it'll check the data that it was expected to receive. The device in the test here is typically VHDL because UVVM is VHDL, but it could, of course, also have a VHDL test bench or Verilog. That works fine as well. It's a Lego-like test harness in the sense that all we have to do here is to connect these verification components directly to the device in the test as you connect any IP, but you don't have to connect those to the sequencer because they're globally connected to the verification components via global signals. So that means you can change your test harness as you like with no changes to the hierarchy, changes to the signals in the hierarchy, sorry. And I would say even a software or hardware developer could actually write test cases because it's quite intuitive. It's on a format that anyone can understand. And of course, there is a documentation for this as well. And if you need to make the changes on the interfaces in a system like that, you can just change the interface and the test bench will run as it did previously because you just access this via transactions or procedures. And another important thing is that all verification components may be controlled from one single test sequencer. That's one of the most important things, I think, with UVVM. That means this sequencer here can issue a command to this verification component, and it issues that command in 0 time. And then of course, it can continue issuing a command to the other verification component, the third, the fourth, and so on, all in 0 time. And that means everything can start at the same time. And also the sequencer can do something else in parallel. So advantages of that is you can have simultaneous activity on multiple interfaces. It's encapsulated, that's important. Everything is inside a verification component. That means you can have reuse at all levels of this verification component. A queue allows you to do multiple high-level commands in a sequence. And local sequencers, I mentioned that already. And what is unique for UVM verification components is that you can control everything from one single test sequencer. And that's so much different from other systems that allow you to control the different interfaces from different processes, for instance, but then passing semaphores back and forth. That works fine if you have 10 lines in 3 different processes. It doesn't work for a real system. You can insert delay between the commands so that you can tell the verification component, do that, then wait 15 nanoseconds, then do that. And that means you can skew the interface actions, so the actions on the interfaces with respect to each other. And that means you can hit corner cases in your system, cycle-related corner cases. You can have simple handling of split transactions and out-of-order protocols, common commands to control behavior, and simple synchronization of the interactions from the sequencer. Also, by the way, broadcast and multicast is possible in this system. That means you get a better overview, maintenance, extensibility, and reuse, as was the target in the first place. There are lots of free verification components as well. So as for the BFMs, there's a large collection of verification components. So these are all available as both BFMs and verification components. Not quite true. The Ethernet is only available as verification component for complexity reasons. They're all free, all open source, and well documented. And there are example test benches. Now we had a few projects in cooperation with ESA, European Space Agency.